Hello learners, welcome to session 4 of Unit 5, Introduction to Abstract Algebra. In this Unit 5, we are looking at complex numbers, and in Unit 3 of the previous session, we looked at modulus and arguments of complex numbers. So through that one, we're able to find when a complex number is given, how to find the modulus or the length, and then also we will also be able to find the argument. So the modulus and argument of complex number we did earlier on the previous session together are what we call polar coordinates of the number, and that determine the number completely. So the polar coordinates determine the number completely. So in this session we are looking at the polar coordinate of complex numbers. By the end of this session you should be able to find the polar coordinates of any non-zero complex number and also express any complex number in polar form. Okay, so the graph above represents a complex number on the OXY plane. So we know that every complex number, let me write it here, is represented as this. It's already there. X equals to Z equals to A plus BI. So when we have that, it can be represented as a point that is AB, and that's why we have A here and then B here. So using the Pythagoras theorem approach, so you can say that this forms a right angle triangle. So we can actually find the cosine of the angle here. So in that instance, you can see that A will be equals to R cos theta. So when you use your basic trigonometric ratios, and then you can also see that your B equals to R sine theta. Okay, so if you are forgetting your ratio, don't forget about that acronyms you were using when you were in senior high, say SOHCAHTOA. You can use that acronyms to find these values. Okay, we can also find the length of Z. That's Z equals to square root of, remember I've already done that one in the previous session, B squared. And we can also find the angle tan theta equals to B on A. Don't forget about your quadrant where it lies. Okay, so based on this you can represent the complex number Z in a polar form. Okay, I've already talked about this, so we have them already. So in that instance, so if I want to put the A and then B into the Z, that's A plus BI, so I get R cos Q plus R sin QI. So, and that's how it's going to be. So you're using Q to be an angle. If you make theta, it's going to be theta. Right, so that's an angle. Okay, let's look at the example. Write the following complex numbers in a polar form. Write the following complex numbers in a polar form. So we have Z equals to 1 plus I. So as usual, we find the first one. Let's look at the solution. We find our R. So R equals to the modulus of Z, and that will give us square root of 1 square plus 1 square. And what do I get? You get square root of 2. I hope you completely agree with me. So far, we can now find the theta of that one. So you can say that tan theta is 1 on 1, which is 1. Therefore, we find theta, the tan inverse or the arctan. So theta equals to arctan of 1, or you can say tan inverse of 1. And what do I get? We are leaving the answer in terms of pi, so I get pi on 4. Or radian rather, we are leaving it in terms of pi or radian. So that's pi on 4. Okay, so therefore we can now write the polar coordinate for this one. So therefore you can see that your Z is now equals to square root of 2, that's R bracket open. Don't forget cos Q or cos theta. So you get pi on 4 plus I sine theta, so I sine pi on 4. Okay, so that's the polar coordinate for z equals 1 plus I. Great. Oh, there's another example here. Square root of 3 minus I. Square root of 3 minus I. So you can find your calculation. First one, so you can find your, let me make it z. So you want to find the first, you find the modulus of z. So the modulus of z is actually equals to r, and you put into square root of a squared plus b squared, you get square root of 4, which is 2. And you find the tan inverse or theta equals to the arctan or tan inverse of, don't forget, it's what, minus 1 on 3, or you can say 1 on 3. Okay, 1 on 3, that's fine. And then let's b on a, don't forget about b on a. And because you can see that z is in which quadrant, you can see z is in 4th quadrant. In that instance, we can find our theta, which equals 2 pi, so in the 4th quadrant, minus the value of the answer you get here, that is the arctan. Okay, I'm using arctan, let me use that one chart. Arctan of 1 on 3, and what do I get? So you get 11 on 6 pi, 11 on 6 pi. Okay, so therefore we want to represent it in polar form or polar form. So in polar form, we can get our z equals to the r brackets open, don't forget about your cos, 11 on 6 pi plus I sine 11 on 6 pi. Thank you. So let's look at this theorem. For any complex number z1 and z2, then one can deduce that the argument of z1 dot z2 is actually equals the argument of z1 plus argument of z2. So you can go to the proof in your book. Very, very interesting, your course material. Alright, so in this session we look at how to write complex numbers in a polar form, and by using the basic idea of trig ratios, you can represent complex numbers in polar form. Thank you for your time, and then we look at the next session.